Good morning, dear students. Welcome to our abstract algebra class. This is the core paper for first MSc Mathematics. I am Dr. J. John Flavia, Assistant Professor of Mathematics, JJ College of Arts and Science, Pudukkottai. Today we are going to see the section 5.6, the elements of Galois theory. Today we are discuss about one lemma 5.6.2. Before that, we see one definition. Group of automorphism. Let K be a field and let F be the subfield of K. Then the group of automorphism of K relative to F, written as G of K, F, is the set of all automorphism of K, leaving every element of F is fixed. That is, the automorphism sigma of K is in G of K, F if and only if sigma of alpha equal to alpha for every alpha belongs to F. Here, the automorphism sigma from K to K is the one-to-one and on-to mapping. Also satisfy the conditions sigma x plus y equal to sigma x plus sigma y, sigma xy equal to sigma x into sigma y. One more condition, sigma alpha equal to alpha for all alpha belongs to F. Okay. Next, see the lemma. G of K, F, that is the group of automorphism, is a subgroup of the group of all automorphism of K. Subgroup means already we studied in UG. We want to prove that H is a subgroup of G. H is a subgroup of G. H satisfies the two conditions. X, y belongs to H implies xy belongs to H. X belongs to H implies X inverse belongs to H. Those a subset H is satisfy these two conditions, then the subset is called the subgroup of G. Next we see the proof. Let F be a subfield of a K so that F is itself is a field. Let capital G denote the group of automorphisms of K. Then G is the group of mapping sigma such that sigma from K to K is one-to-one and on-to mapping, and also satisfy the condition sigma x plus y equal to sigma x plus sigma y, sigma xy equal to sigma x into sigma y. These are the definitions of automorphism. Next we define the set G of K, F, that is the group of automorphism. Collect the automorphism sigma belongs to G such that sigma x equal to x for all x belongs to F. So clearly G of K, F is a subset of G. We want to prove that G of K, F is a subgroup of G. Already we said the property of subgroup. Take two elements from H. The multiplication is also belongs to H. One element from H. Then the inverse element also belongs to H. So we apply the property. Let F, G belongs to G of K, F be arbitrary. Here G of K, F is the collection of all automorphism. So F and G are also a automorphism. Then F and G are automorphism of K such that f of x equal to x and g of x equal to x for all x belongs to F. F and G are automorphism of K. So F from K to K, G from K to K. These two mappings are one-to-one and on-to mappings. Also satisfy the condition f of x plus y equal to f of x plus f of y, f of xy equal to f of x into f of y. Similarly, g of x plus y equal to g of x plus g of y, g of xy equal to g of x into g of y. Next we find the product group Fg. So Fg is also from K to K mapping. This is 1 to 1 and on to mapping. Next we have to prove that Fg of x plus y equal to Fg of x plus Fg of y, Fg of xy equal to Fg of x into Fg of y. So first we see that Fg of x plus y. Fg of x plus y can be written as f of g of x plus y. G is an automorphism. Then g of x plus y can be written as g of x plus g of y. This is from 2. F is also automorphism. Therefore, f of g of x plus f of g of y can be written as f of g of x plus f of g of y. F of g of x can be written as f of g of x. F of g of y can be written as fg of y. Therefore, fg of x plus y equal to fg of x plus fg of y. Next we see the multiplication. Fg of xy. Fg of xy can be written as f of g of xy. G is an automorphism. So g of xy can be written as g of x into g of y. F is also automorphism. So f of g of x into g of y can be written as f of g of x into f of g of y. F of g of x can be written as fg of x. F of g of y can be written as fg of y. So from this we can see that fg from k to k is the 1 to 1 mapping. Also satisfy the condition fg of x plus y equal to fg of x plus fg of y. Fg of xy equal to fg of x into fg of y for all x comma y belongs to k. The another one condition we have to prove that fg of x equal to x. So next we see the result. Fg of x equal to f of g of x equal to f of x equal to f of x equal to x for all x belongs to f. So the product automorphism fg satisfies the automorphism conditions. Also fg of x equal to x. Therefore, the fg element belongs to g of k comma f. Therefore, fg belongs to g of k comma f. First condition is over. Next, we prove that f belongs to g of k comma f. Then f inverse belongs to g of k comma f. So next, we define the inverse automorphism. F inverse from k to k is the 1 to 1 and on to mapping. Here we assume f of x equal to x dash, f of y equal to y dash for all x comma y belongs to k, x dash comma y dash belongs to k, and f inverse of x dash equal to x, f inverse of y dash equal to y. We define the inverse mapping like this. Next one, f of x plus y equal to f of x plus f of y. We already know that f is the automorphism. So f of x plus y equal to f of x plus f of y. Right hand side, f of x equal to x dash, f of y equal to y dash. We substitute this value, we get f of x plus y equal to x dash plus y dash. This implies x plus y equal to f inverse function of x dash plus y dash. Next, consider the inverse function f dash of x dash plus y dash. F inverse of x dash equal to x. We already defined the value. So f inverse of x dash plus y dash equal to x plus y. X is nothing but f inverse of x dash, y is nothing but f inverse of y dash. Apply this value, f inverse of x dash plus f inverse of y dash. So we get f inverse of x dash plus y dash equal to f inverse of x dash plus f inverse of y dash. Next we see the product f of xy. F is an automorphism. So f of xy can be written as f of x into f of y. We define f of x equal to x dash, f of y equal to y dash. So apply this value x dash y dash. So we get f of xy equal to x dash y dash. This implies xy equal to f inverse of x dash y dash. Next, consider the inverse function f inverse of x dash y dash. We know that f inverse of x dash equal to x. So f inverse of x dash y dash equal to xy. Already we defined f inverse of x dash equal to x, f inverse of y dash equal to y. Apply this result. We replace x by f inverse of x dash, y by f inverse of y dash. Therefore, f inverse of x dash y dash equal to f inverse of x dash, f inverse of y dash. From this, f inverse is an automorphism from k to k. The remaining one proof is f inverse of x equal to x. Next we see the proof. If x belongs to f, then f of x equal to x. From this, f inverse of x equal to x. So, the inverse function satisfies all these conditions. Therefore, f inverse belongs to g of k comma f. Thus, we have shown that f inverse from k to k is 1-to-1 and onto mapping. Also satisfies the condition f inverse of x dash plus y dash equal to f inverse of x dash plus f inverse of y dash. F inverse of x dash y dash equal to f inverse of x dash into f inverse of y dash. Also, f inverse of x equal to x for all x belongs to f. This implies f inverse is an automorphism of k. Therefore, f inverse belongs to g of k comma f. So, g of k comma f satisfies the property of subgroup. Therefore, g of k comma f is a subgroup of g. This is the proof of the lemma. Thank you, students.